Hello everyone, my name is Sergio Sevillano. I'm a postdoctoral researcher in University of Durham, in IEEE specifically. And well, as probably you know, today I'm going to be talking about CMB bounds on accreting extended dark matter objects. This talk is based on my first paper in IEEE that I did with Juna Kroon and receives the same name. Now, in this project, what we are going to be doing is studying one of them, well, a quite popular candidate for dark matter. Now, we are very used to all the different candidates that we can have for dark matter, as probably you have worked with some of them. But one of the most curious ones, or probably popular ones, are these composite microscopic dark matter candidates. And perhaps the most famous one is primordial black holes. And they have, well, you form the singularity, and because we are not going to be able to see it because it's a black hole, it will give the rotation curve that we are looking for. However, in most of the cases, it is possible that you can create also a massive object but doesn't have a PBH inside. And that is exactly what we call these extended dark matter objects. They can be, for example, scalar fields with some disposition. And the most important thing that you need to have in mind in this case is that they behave as primordial black holes in most of the cases on the rotation curves and most of the phenomenology, but they don't have a black hole inside. So that's the only thing that you need to know. There are some examples for these kind of objects that are quite popular. For example, is the uniform sphere. You see the uniform in this plot is the red line. This uniform sphere basically has constant density inside. Then you can also have, for example, boson stars, where the boson stars are given by the yellow-orange line, depending on how you see it. And what they have in this case, they are calculated by having just a quantum field collapsing under under its own gravitational potential, and you get this specific shape for the matter profile. You can also have the famous Navarro-Frank-White subhalos. So well, we are used normally to having this kind of subhalos of the size of a whole galaxy, but in this case, they can be smaller and they can be just disposed in the galaxy in the same way that PBHs usually do. And the last one that, for example, I give as an example, are these ultra-compact mini halos that are this dark green one. And these ones actually are quite interesting. I'm not going to show much about them, but are interesting because normally you know that the famous primordial black holes, they are always formed when you have overdensities in the early universe. You have an overdensity of some scalar field, and because it collapses in recombination, in the end what you're going to have is the creation of these primordial black holes. However, there must be some threshold in which you cannot actually form a primordial black hole. So you must have some relic that has a lot of mass in it, but doesn't have a primordial black hole. Well, that is the case for these ultra-compact mini halos. So yeah, they are very interesting, and also they are going to look different, however, depending on how you form these kind of objects. Now, these objects have been studied quite widely already, and mainly this has been done in terms of microlensing. So the same microlensing signals that we have from PBHs, you can do them for EDOs. And the most interesting thing is that, of course, you have to do one run for different shapes, but not only do different runs for different shapes, but also for different radii, because depending on how big is the object, you're going to find one thing or another. And you may imagine that you can always take whatever solution you have from PDHs and adapt it to these kind of objects, but that's not usually the case. As you can see for lensing, you end up having these peaks over there that they call caustics. And that happens because there is some sort of resonance taking place in the light rate trajectory. And when you have that into consideration, you find those non-trivialities. So that's why it's important to actually repeat all the phenomenology that we know from PBHs with these kind of objects and see how it will differ for each kind of shape that you may consider. Now, in particular, the kind of constraint that we are going to do in this talk is going to be the accretion and the impact that the accretion has on the CMB. So as you know, this has been done already for PBHs, is this big kind of wall on the right. And I actually really like this plot particularly because you see that you have like this wall on the right and also you have the wall on the left. As you may understand here, there is no, we are not going to have the evaporation wall for EDOs because as there is no singularity, there is no evaporation. However, we should predict still having this wall on the right of accretion. And that is exactly, well, we know that it's not there, so we are going to try to derive the new constraints, but for these kind of objects. And I'm going to be honest with you, this is not the first time it's been done. Actually, the same calculation was done a few years ago by Bei, Long, and Lu. But the thing is that they only consider one type of EDO, the one that was a uniform sphere. And the reason I believe they did that is because they solved the whole system analytically, which is very convenient and is very fast to do. But the problem is that you cannot extend these results to other type of shapes. And also, for some reason that I don't really know, they only considered the 100% of dark matter fraction. This means that all the dark matter is given by this kind of EDOs. However, you see that in all these, well, in all the previous plot that I showed you before, there was, you always plot them by showing, you see here, the fraction of dark matter, allowing for different sources of dark matter around. But the problem is that if you want to basically get the new bounds for these two plots, for NFW on boson stars on any other shape, you will have to solve the whole system numerically, which is quite difficult. And also, that will allow us to change for any dark matter fraction. That's exactly what we are doing in this talk. Okay, so in order to do that, the first thing that we need to know is what is going to be the background at infinity. So we are going to place these kind of EDOs in our universe, and we're going to see how these EDOs are going to change the recombination history in our universe. So for that, we first need to know how the universe is going to evolve. And for that, we're going to use these two equations over here. One has the temperature, and the other controls the ionization fraction of the whole universe. It has a lot of physics in this. I won't go through it because it's not very important. The most important thing is that you will get this kind of shape. So you see that this goes with redshift, and it goes, the ionization goes from 1 as we expect, and as the universe starts cooling down, you end up hitting this plateau over here. That is where we kind of live today. So the ionization fraction today is around 10 to the minus 3, 10 to the minus 4. And the temperature, of course, as you understand, it goes just down. And we are going to take, at infinity, the density of baryons, basically, as being given by the mass of baryons times the number density of baryons. That's quite intuitive. Then the temperature at infinity given by this function, and the ionization at infinity given by that other function. And once we have that, the picture is going to be the following. You see here, I'm going to show you some CGI. I got Christopher Nolan to do this. What you see here is a lot of matter, and there is an EDO actually here. Now we can see it because, as you may understand, it doesn't interact with light. However, there is going to be these protons, these electrons, these hydrogen, so protons and electrons already recombine. And with some time, what is going to happen is that they are going to start feeling the gravitational pull of this EDO. So they are start going into the center. And because now there is more density inside, it is going to start heating up the environment, and this heat is going to start emitting radiation. And that is exactly what we want to test. This radiation that suddenly shouldn't be there in the standard cosmology case, now is going to have some effect on the evolution of the universe. We are going to look at how, what is the impact on the evolution of the universe, and try to constrain that. So the lack of observation of that modification is going to give us some bounds for these kind of objects. In order to calculate all this shape that we expect of the accretion of baryonic matter into the EDO, we just need to study 4 different quantities. That is the density of matter, basically how it changes with space, also the temperature, the ionization fraction that I mentioned before, because as you may understand, when all the matter starts accreting inside the EDO, the temperatures will go up, and so you will be able to ionize some of this already recombined hydrogen, and also the number of free electrons and protons, which we give for granted to be the same. All of this, as we are going to map it using some kind of fluid. For that, we have to use Navier-Stokes equations, and as you may understand, we cannot solve these equations exactly. In order to be able to solve the system, we need to take some approximations, and these approximations are the following. First, we assume that we are going to study a static solution. Then we will also take the hydrostatic approximation, which means that there is in these stable solutions there are no flows of matter. This, for example, already kills any PBH in the center, because as you understand, the PBH is kind of like a sink. So you may have some stable solution, but in this stable solution, you always have matter falling inwards. In this case, because we don't have a primordial black hole inside, or any black hole inside, what is going to happen is that the pressures can compensate the gravitational potential. So actually you can have some static solution that doesn't have any flow, radial flow going in or going out. Also, we are going to assume that the ionization fraction is constant in space. Now, you may, of course, this is not true. It's going to change the ionization fraction once you start going inside the EDO. But we are going to do that for the meantime, and then account for this after. And after that, and finally, we are also going to allow for adiabaticity. This is just a simple condition that what it says is that there is some kind of power law relation between pressure and density of the baryonic fluid. And this makes our calculations much easier, because now we can also relate the temperature to density. Once we have that, the very complicated equations that we had before transform into this very simple, well, it's not actually simple, but kind of simple equation. Now, you see that here, gamma, we are going to take it to be a constant. However, once we start changing some of the, for example, the ionization fraction, we need to take into account that the value for gamma is going to change. So as long as the ionization fraction is constant, gamma is constant. So that is something that we will also have to add later on in the whole calculation. Now, well, I'm going to disappear for a while while I show you these kind of things, but the whole thing that I'm going to show you are in these 4 plots. So you see that at infinity, it goes to this asymptote that is the solution at infinity, and then the EDO starts, well, it's in the origin, and this is a radial plot. Actually, I think that I'm going to add me there. That is much better. So I'm a little bit small, but that should be fine. And this is the solution for a uniform sphere. This is just the example that I showed you. And you see that this is the number density, this is energy density, temperature, and ionization fraction. As I said before, ionization fraction is going to be constant. I plot here different radii, that's not very important, and also 2 different sets, 2 different redshifts. So that's why one of them starts and go to, well, some solution, and the other at infinity goes to a different solution, because the solution at infinity is changing with time, as you already know. Now, this is the solution that you get when solving that equation. Now we need to add some better, well, add some corrections to get a full picture of what is going on. The first correction is interactions with the CMB. When we took this static approximation, we basically killed 2 of the Navier-Stokes equation that we maybe, it will be better to actually consider. In this example, as you can see, we have some, the radius of the object over here, but we have a different radius that forms when you have accretion. And that different radius is the boundary radius, which is defined as, this is very similar to the Schwarzschild radius, but instead of having there the speed of light, what you put is the speed of sound of the fluid at infinity. So that boundary radius corresponds to actually this radius over here. It's kind of like the impact that the EDO has on matter. After this point over here, actually matter behaves as the solution at infinity. But inside this radius, it feels the pull of the EDO or its existence. Now, if you have now some interactions with the CMB and the CMB tends to cool whatever is happening inside the EDO, that is not going to affect the number density of electrons or the energy density of matter. Of course, that is not going to be affected because this is just affects the temperature. So we should see some difference in this lower plot over here. And what that is going to do, you can calculate the new radius is going to become smaller, and well, you get some interactions, it becomes smaller and defines a new radius over there that we are going to call R cool. And you can see what happens here, that basically some of the solutions go more into the center, because the higher temperatures that you have outside at infinity, the more interactions you are going to have with the EDO. So that's why at higher redshifts, you get more interactions. Also, we are going to take into account the collisional ionization. What this does is that when you have hydrogen being formed inside the EDO and you go above some temperatures, this hydrogen is going to start colliding with each other, and that is going to ionize one of these hydrogen atoms. And in the end, what it's going to do is that the ionization fraction will go up. That takes place like this. So you see here that suddenly, before we had it constant, and now it goes up and then goes to 1, because that's the maximum you can have. And finally, we will also put the relativistic effects, because at some temperatures, as they become very, very large, electrons will become relativistic, and they will contribute differently here to the internal energy. So that's why here you have some slope, and after this point, you get a different slope. That's everything. So once you have these plots, that's the disposition of how matter is kind of getting around the EDO. We have all the information that is necessary to know the luminosity that will go back into the background. Now, if we want to know what is the luminosity being put on the background, first, for that, we just need to calculate how you would emit photons in this process. And the most important channel is going to be the electron-electron interactions. So for that, we have to do just calculate the Weierstrass line for that, and this is the emissivity. It's not very important. Probably some of you already know these equations, but it's not very important to go into detail. The important thing is that when you integrate this whole thing with all the different frequencies and all the different radii that you have inside the system, you get the total luminosity. And once you have the total luminosity, you can average with respect to all the different relative velocities. This was actually very difficult to code, and I guess that is the reason why analytically was not able to be done. And you get this kind of plots over here. And this plot, what it's showing is the different luminosity that you get from different objects at different redshift. And what is quite interesting here is that you can actually take the uniform sphere and shift it so that you get the solution for other objects. So what this is saying is that actually we don't need to repeat the same calculation every time. We can actually just find we need to find some kind of rule in order to know what is going to be the necessary shift and just take the existing constraints and apply them into the new objects. We will see later how that actually comes through. Now, if we already have this luminosity, we now can actually calculate the impact that this luminosity will have on the background. For that, we calculate in some other way how much of this energy gets deposited into the background. We put it into the equations that I showed you before. I don't know if you remember these equations, but these two new terms have mu, and these two new terms are going to be the ones who modified how the whole universe is evolving and how the recombination history is taking place. That creates the following difference. So this blue line over here is the line that I showed you before, so that is a standard lambda CDM, and the new lines that you see over there are the ones that are changing the recombination history. You see that the change is very, very small, but still this very, very small change is making a huge difference. Now, when we take that difference and we create some rules in order to know what is going to be constrained or not, basically we are taking that this difference cannot be bigger than 10 to the minus 4, you find actually this kind of plots. And this is the plot that I showed you before, but now you can vary this plot for the uniform sphere for different dark matter fractions and also create these fancy plots that we are interested in. We can put the different dark matter fractions and also the different masses, and now we get the new constraints for different radii. This line that you see over here, this line is the constraints for EDOs that are already dense enough, so dense that they would create a black hole by themselves. So this shows the limits of our calculations. Everything that is kind of, well, closest to this left line would be completely wrong because our calculations, our approximations are not valid anymore, and things that are close to this line, well, are starting to be problematic. So probably this yellow line that you see around here is in that limit. Now, when we combine or repeat this whole thing with this other new NFW subhalo and boson star, what we find is what we expect. New bounds, the bounds actually depend on what object you're studying, and you can combine them with the already existing constraints over there. Now, there is a major difference that is quite interesting with PBHs, and that is that with PBHs, well, this gap is kind of famous because it's a gap that is not being constrained so far. And well, that is the only gap, and there are new research trying to constrain this gap and close it. However, we see that for EDOs, we have that gap, well, that actually goes to infinity on the left, but also we have now a gap existing in here, which something will have to come, new constraints, probably they are already around, and we can calculate them to close that gap over there. I hope you enjoyed this talk and you got something out of it. The most important thing that you need to see is that we can constrain these kind of objects also using CMB accretion, and we can do it following these rules. Now, the important thing is that we have put this code outside, so in GitLab you can find some code, so that if you have any kind of shape in your head that you want to constrain in this similar way, you can easily do it. You just have to put the shape into the code, and the code will do all the calculations necessary to get you to this kind of fancy plots that I've shown you all along. So I hope you enjoyed it, you learned something along the way, and I hope to see you the day of the discussion. If you have any question, just drop me an email and I will be happy to answer it. Goodbye.